This is the video lesson for 4-3 Day 1. A little math humor for a moment. In the lesson today, we're going to talk about inverses and go back to some ideas from pre-cal and before, and then tie them to the calculus. You may want to watch this more than once to get those connections instead of just saying, I don't get it. Okay. So as we talk inverses, we're going to give you a little recap. So a function and its inverse function can be described sometimes as a function that does something to one number, and then the inverse function undoes that and takes you back to where you started. I've got a graph for you. I guess we'll take this down. I've got a graph for you. On the graph, I've got a blue function that would be f of x. And then its inverse function, the one in which I'd switch x and y roles, input and output roles. Notation, we're going to have to be a little bit careful with. We're so used to doing f prime that we're really going to have to think about when we want an inverse and when we want to show a derivative. So this is f's inverse of x would be the red graph that you can see. The green line, that's y equals x, that's the reflection line that all inverses end up flipping over. In other words, the role of input and output is switched, so the graph of a function and the graph of its inverse are always flipped over that y equals x line. When you wrote inverse functions, you took the y and the x and you switched them. When you switch the y and the x, something else happens that makes some sense. On the blue line, the slope is 2, meaning 2 over 1. When I switch the roles of x's and y's, that would take y's from the numerator in the slope and put them down in the denominator for the slope of the inverse. So the red line's slope then is not negative 1/2. It's not perpendicular to it. It's quite literally the reciprocal. The y's became x's and x's became y's, so the slope for my inverse function is its reciprocal of what the slope was for the original function. So one thing that some calculus teachers talk about is anytime you're talking about inverses, you want to think about ordered pairs on inverses flip. So 0, 3 becomes 3, 0 on its inverse, and their slopes are reciprocals of what they would have been at those points. Trig functions, which is where we're going to look today, trig functions have two notations for their inverse. You saw last year both notations. So inverse cosine can be written as cosine with that negative one, that inverse inside, and also arc cosine. So either one, and your book will use both, and I'll use both. So last thing on this slide, we want to keep in mind that when we're looking at inverses in general, whatever our inverse equation is, that our input becomes the output of the inverse, and that the output from our original becomes the input to our inverse. So for cosine, the input is usually an angle, and the output is the ratio of that angle. Think right triangles. For inverse cosine, then, we input a ratio, and it outputs an angle where that ratio occurs. Now with trig inverses, it's not always a perfect system. There are several angles that have a specific trig ratio. Inverse cosine only gives specific ones. And you knew those domain restrictions, and we'll look at them briefly today. They won't be a huge deal. So let's take what we're just hearing again and put it together on one that looks a little bit more like calculus. So I've got a red graph of the function f of x. It's a part of an x squared graph, and on it is the ordered pair 2, 4. If I was asked about the slope of its inverse function, here's what I would know. I would know that the blue curve is its inverse equation, f inverse, and I would know that 4, 2 exists on it. And here's what else I would know. Whatever the slope is at 2, 4, and I went and calculated it, took the red function's derivative, which is 2x, and evaluated it at x is 2. And the slope of the curve right there, the slope of the tangent I would put in, is 4. If I go to not the same x value on the other one, but the 4, 2 point, the point whose coordinates are input, output flipped on my inverse function, and I do the derivative of the inverse function and evaluate it at that point, the slope comes out 1/4, because again, x's and y's have switched, so our role of input and output, our role of slope then gets flipped upside down. So the big takeaway is on my inverse function, my slopes are reciprocals. Not opposite reciprocals, just reciprocals, because y's and x's switched. Okay, my delta y's now go to the denominator, my delta x's now come to the numerator. So big takeaways. If graphs or functions or just equations are inverses of each other, if f passes through a certain point called AB, then I know that its inverse has to go through BA. At those 2 points, if I were to take the derivative of the first one would be the slope at AB, the derivative of the second one would be the slope at BA, and their slopes would be reciprocals of each other, because I'd be switching the y and x in my slope. So because of that, they put in this theorem. And the theorem in calculus language is a little tough to understand. They're talking about f as a differentiable equation at every point on some set of x values. So over an interval of x values, maybe it's 0 to 10, maybe it's negative 2 pi to pi. Doesn't matter, but over whatever interval they're talking about that f is differentiable, f has an inverse that's also differentiable everywhere in that interval, as long as the derivative of f, the slope on the original f function, is never 0 in there. If the slope's 0 somewhere in that interval of your original function, then there's no reciprocal. And therefore, at the other point on your derivative function, there wouldn't be a value for your inverse function. So how are we going to find the derivatives of these trig functions? You have derivatives for your regular trig functions. Now we need it for the 6 inverse trig functions. So I want to take you back to one of your Pythagorean identities. You have a Pythagorean identity that said sine squared plus cosine squared of y equals 1. So if I move that around, remember, pause the video to move that around if you need to. If I move that around, I can use one of 2 forms of this in what we're going to do today. If I move it around, I can get cosine of y to be equal to 1 minus sine squared of y. I would subtract, take some square roots. I can also get sine of a particular y value to be the square root of 1 minus cosine squared of that same value. These are going to be substitutions that we use today to come up with the trig derivatives, the inverse trig derivatives. So we're going to do 3 things to derive some of these inverse trig derivatives, and we're going to give you the rest of them. So first thing you're going to do is a little rewrite on this equation. If this is truly an inverse sine function, then I should be able to rewrite, not do the derivative, and say then x should be equal to sine of y. Not inverse sine of y. Once I switch it back, then I'm back to the sine function. I'm going to use that implicit differentiation where we have 2 different variables, but we're doing the derivative. So the derivative with respect to x on that side is 1. The derivative with respect to x on this side would be cosine y dy dx. My goal is to get that derivative function all by itself. So when I move this around, I'm going to have dy dx, the derivative of the function, or the equation actually, being 1 over cosine y. You say, oh, that'll be easy to remember. We don't want it in terms of y's though. Whenever we're dealing with these inverse trig functions, you're going to have inputs of x, locations on the graph. So we really want this in terms of x and not 1 over cosine y. So when we go to get the derivative for that function, we're going to need to do some substitutions. Instead of 1 over cosine y, I'm going to go over to my substitutions over here and say, oh, well then I could rewrite that as 1 over the square root of 1 minus sine squared y. Seems like it got more complicated, but we're still in y's. Going back up to where we started, sine y is x. That's a fact we have. That's the initial equation we were actually trying to find an inverse of. So when I have sine squared of y in here, I can replace that with an x squared. So the derivative now in terms of x for inverse sine is 1 divided by the square root of 1 minus x squared. So there's our derivative for inverse sine. Not as easy as the derivative for regular sine. Well, we can do it. And do the same thing again on cosine. So try it. Try to see if you can do it with me as I do it. I'm going to do a function rewrite. If this is truly an inverse function, I should be able to get back to an identical function worth the same by swapping them out and making it into cosine y. So that's an identical function. Little implicit differentiation. So on one side, the derivative of x is 1. On the other side, derivative for cosine is opposite of sine of y. dy dx, because I'm trying to derive with respect to x, since we always like to plug in x values into our derivatives when possible. Getting dy dx alone, I'd have a -1 over sine of y in my derivative. Then we're going to do a little substitution and replacement with some trig values in hopes of getting back to this being in terms of x. So it's going to be -1 divided by, instead of sine of y, I can put in 1 minus cosine squared of y. And if I go back to the original equation, original function, and you notice we're doing that a lot, replacing things, then I can say that this is, the derivative is -1 with the square root of 1 minus x squared. So derivatives for your inverse sine and your inverse cosine function. All 6 of these trig derivatives that you can see right here, I have a small piece of paper for everybody when you're actually here so that you can have those on paper, but you need to eventually know them, and you will. There's a pattern to them. When the u's are in here, the u is just an embedded function, so the u is in there. Think about chain rule, okay? So when they actually say du dx, that's in there in case we have an embedded function, so that du dx is for chain rule. To just remember to do that. Okay, there are some domain restrictions for your inverse trig functions. And so let's just look at the first 3. These should come back to you from pre-cal. The inverse trig functions, one takes in values between -1 and 1, because it takes in sine values, and it gives out, range-wise, -pi/2 to +pi/2. Cosine then, inverse cosine, takes in values between -1 and +1, the ratio, and gives out an angle between 0 and pi. And you had all these last year. Inverse tangent then takes in any number as the tangent ratio and gives out a value, an angle between -pi/2 and +pi/2. Mostly you just want to be aware that there's some restrictions on what comes out of those inverse trig functions and what can go into them in the first place. I would keep that sheet of 6 handy as we do all these derivatives. I put up in the corner what the derivative is, but these are ones you're going to need to know, so you want to get working on thinking and finding a pattern to those. So you want to find the derivative of inverse sine of 2x plus 1, the quantity 2x plus 1, because this might model something that we need an acceleration or a velocity for. So in order to get derivative, we're just going to go straight to the pattern. It says, oh, you want the derivative here, okay, dy dx. Well, for any inverse sine function, it's going to be 1 divided by the square root of 1 minus the embedded function, that u function, squared. So we're thinking about this as our u. And then du dx, we need chain rule, the derivative of that embedded function, which in our case would be 2. There's lots of different simplified forms for these. We're going to go for a little bit of simplification and then done. I'm not going to multiply that out too much. And there's our derivative. So if we needed to calculate velocities for that function, there's our derivative. All right, come down and do the next couple with me. Pause the video at any point that you want to try it yourself and see what you can do. Anytime you have an embedded function, you want to think about that as the u that the derivative is referring to, so that we can do this of a function that's got more than an x in there. So for inverse cotangent, its derivative is going to be -1 divided by, there's no square root here, 1 plus our u quantity squared times du dx, the derivative of our embedded function with respect to x. There's lots of ways we could simplify this one pretty quickly and pretty easily. So you could come up with all sorts of stuff in here that you could do to them and have lots of different simplified forms. So if you see them looking different in the key, stretch your simplification skills out a little bit and do some algebra and see if you can get them to match. And this last one, with the secant and the cosecant function, you've got an absolute value in its derivative, and it needs to stay there unless we know that the function that you're putting in there is always positive. If we know it's always positive, then we could remove the absolute value signs. But if we don't, we need to leave them so that mathematically we have the correct derivative. So dy dx, it says the formula for it's going to be 1 divided by the absolute value of our u expression times the square root of our u expression squared minus 1 multiplied by whatever our u expression's derivative is. And so for this one, again, lots of different forms we could get this to by cleaning up the denominator. Consider that when you check answer keys. Consider that if you had multiple choice, you might want to see what kind of square root things we can get out of the denominator there and simplify that a little bit more. There are plenty of other simplified versions of that. All right, last thing that I'm going to do with you, and then you can try a couple extra if you would like, is the position function. Let's actually do some calculus with this. So if a particle is moving along the x-axis, so its position at any function in time is given by x of t. This is our position time function, and it's an inverse trig expression. They would like to know its velocity, its rate of speed with direction at time is 3. So first we need a derivative, and then we'll see what's happening at time 3. So if we want velocity, we're going to need to take the derivative of the position function. Since it's an inverse sine function, we know that there's a formula for that. Again, get your formulas out if you need to. It's going to be 1 divided by square root of 1 minus, in our case, t over 4 is our embedded function, squared, times t over 4's derivative, which is 1/4. So I don't need to clean this up too much in the sense that I'm just going to use it to evaluate the velocity at a position in time. So I don't need this cleaned up too much, but that 4 really belongs in the denominator. So there's our velocity function. And we're interested in the velocity at a time of 3. So our velocity at 3 is going to be 1 divided by 4 times the square root of 1 minus 3/4 quantity squared. Okay. And yes, without a calculator, you can do a little bit of work to get this to a reasonably simplified value. Okay. We'd have 1 over, and this becomes nothing about calculus. So we'd have 1 over 4 square roots of 7/16. And eventually, again, doing some square root work, pulling out that 1/16, eventually you could end up there. You don't need to simplify it too far, but be aware of the possibilities for that simplification. All right, these last two, you try them. There are lots of simplified forms. I'm just going to get you to one form. So pause the video, try them yourself, and see, and then come back when you're ready to see them. If you're back, that means you're ready to see these, but you've tried them yourself. So without doing a lot of simplifying, this is one of the forms that you could have come to. Be careful where you park some of the values that have negative exponents on them, keeping in mind that the 6 does not have a negative exponent on it. So that would be one form of that derivative. On this second one thing you notice is that they told you that x is greater than 0. They told you this for a reason. The reason is, if you know x is greater than 0, it means x is positive. Even if you didn't know that, x squared plus 1 has to be positive, even if you didn't know x was greater than 0, because x squared is going to be 0 at the very smallest, add 1. So when I go to do the derivative, you're going to notice that I dropped the absolute value in this one because there's no way that the expression in the absolute value could be negative. Do a little bit of radical cleaning up so that you can get it to this state. Okay, so you'll need to clean up inside that radical a little bit and pull out an x squared factor from the radical to cancel with your numerator x. And finally, this is your assignment, okay, the problem numbers, and we'll see you next week.